5.21. A magnetic dipole is under the influence of two magnetic fields. The angle between the field directions is 60 degrees and one of the fields has the magnitude of 1.2 into 10 raised to minus 2 Tesla. If the dipole comes to stable equilibrium at an angle of 15 degrees with this given field, what is the magnitude of the other field? Now, when two fields are there and the angle between these two fields, that is 60 degrees, and dipole moment that is in stable equilibrium with B1. Now, when two magnetic fields are there and dipole moment is placed in the field, means it is under the effect of two torques. One torque is exerted by field B1 and another one is exerted by field B2. And when these two torques becomes equal, then this will remain in equilibrium. Okay. So torque due to field B1, that we can write MB1 sine 15 degree here, and that you have to replace by M. And the torque due to other field B2, that is MB2 sine 45, because the angle between B1 and B2, that is 60. Angle between dipole and B1 is 15. So obviously the angle between dipole and B2, that will be 45. M will be cancelled from both the side. And now substitute the value of B1, that is 1.2 into 10 raised to minus 2 Tesla. And sine 15 degree, that is 0.26. Take that value from the log table. B2 that we have to calculate, sine 45, that is 1 upon root 2, that is 0.71. And solve it, you will get value of B2. Clear to all of you? 5.22. A monoenergetic 18 kilo electron volt electron beam initially in the horizontal direction is subjected to a horizontal magnetic field of 0.04 Gauss, normal to the initial direction. Estimate the up or down deflection of the beam over a distance of 30 centimeter. Mass of electron, that is 9.11 into 10 raised to minus 19 coulomb. Okay. Now this note, that is not important for us. Now see here. This one is the region of magnetic field. Electron beam is entered in it, and due to the magnetic field, it will experience the force. So now it will move on the curved path. So when it cover the distance 30 centimeter in the region of the magnetic field, then what will be its deflection with respect to the original direction of propagation that we want to find. So here we can consider the motion or the velocity that is in x direction. So the deflection that is in y direction. Okay. So first of all, here we have to calculate the velocity of the electron, because when we calculate velocity, then after we will get the force acting on the electron as per equation F equal to BeV. And once you get force, then you can calculate acceleration. Okay, and force that is perpendicular to the velocity, under the effect of which the acceleration produced will be also perpendicular to this initial velocity, and therefore it will be deflected. Now see, kinetic energy that is given to you 18 kilo electron volt. So 18 kilo, that is 10 raised to 3, and convert it from electron volt to joule by multiplying with 1.6 into 10 raised to minus 19. Kinetic energy, that is half mv square. So we can write half mv square equal to 18 into 1.6, and this 10 raised to 3 and 10 raised to minus 19 will give you 10 raised to minus 16 joule. Clear up to this one? Now here make V as a subject of equation. So 2 into 18 into 1.6 into 10 raised to minus 16 divided by mass of electron, that is 9.1 into 10 raised to minus 31 whole raised to 1 by 2. And when you solve this one, you will get velocity, that is 8 into 10 raised to 7 meter per second. Now magnetic field given to you, that is 0.04 Gauss, so that is 0.04 into 10 raised to minus 4 Tesla. So we can write that is 4 into 10 raised to minus 6 Tesla. Now horizontal velocity, that will remain constant. So when the distance is covered equal to 30 centimeter, then we can calculate the time taken by electron to cover the distance equal to 30 centimeter. So time t, that is d by v, d that is 30 centimeter, so 0.3. Velocity we calculated previously, that is 8 into 10 raised to minus 7. So you will get here 3 by 8 into 10 raised to minus 9 second. Actually, you will get 10 raised to minus 8 seconds, so rectify it. Now, the time during which it covered 30 centimeter distance in horizontal direction, in the same time interval, its deflection also takes place. Suppose its deflection, that is y. Then we can use the equation deflection y, that is v0t plus half at square. But we don't have acceleration. So acceleration, that is force upon mass. And we know this thing, when any charge q is moving in the magnetic field with velocity v, then the force on it, that is qvb. So as per that, we can say force on electron, that is evb. So substitute this value evb here. Now electron enter in the magnetic field in x direction. So initial velocity in y direction, that is 0. So you can write y, that is half evb upon mass of electron into t square. Now substitute the values. So y, that is half into 1.6 into 10 raised to minus 19. V, that is 8 into 10 raised to 7. B, that is 4 into 10 raised to minus 6. Time, that is 3 by 8 into 10 raised to, take here minus 8 and square of 8, and then mass of electron, that is 9.1 into 10 raised to minus 31, and then solve it, you will get deflection of electron beam. Clear to all of you? 5.23. A sample of paramagnetic salt contains 2 into 10 raised to 24 atomic dipole, each of dipole moment 1.5 into 10 raised to minus 23 joule per Tesla. The sample is placed under a homogeneous magnetic field of 0.64 Tesla and cooled to a temperature of 4.2 Kelvin. The degree of magnetic saturation achieved is equal to 15%. What is the total dipole moment of the sample for a magnetic field of 0.98 Tesla and temperature of 2.8 K? So here the magnetization of the sample takes place. 15% of saturation magnetization. Saturation magnetization means maximum magnetization, and that will be achieved when all the dipole moments are aligned in the same direction. Okay, now see here. Total number of magnetic moments given to you, 2 into 10 raised to 24. Each one that is with value 1.5 into 10 raised to minus 23 joule per Tesla. Okay. Now, initially this one is in the magnetic field 0.64 Tesla at a temperature T0 equal to 4.2 Kelvin. And 15% of the sample is magnetized. So first of all, we have to calculate its maximum possible magnetization. So when all the dipole moments are aligned in the same direction, then the resultant magnetic moment induced, that is the resultant magnetization, and that will be the maximum one. So M maximum, that is number of dipole moments into each dipole moment. So 2 into 10 raised to 24 into 1.5 into 10 raised to minus 23. So you will get maximum magnetization, that is 30 ampere meter square. Now, sample is magnetized 15% of this one. Now we can use Curie's law here. Magnetization of the sample in the given magnetic field at given temperature, that we can give M equal to C B0 magnetic field upon T0 the temperature. Magnetization of the sample, that is 15% of maximum magnetization, that is equal to C B0 T0. Now we want to calculate the total dipole moment of the sample, means the magnetization of the sample at this magnetic field and temperature. Now we can write another equation as per Curie's law. M dash, that is equal to C B0 dash, the new magnetic field, which is 0.98 Tesla, upon T0 dash, the new temperature 2.8 Kelvin. Now take the ratio of this to this. So we can write M dash by M, that is B0 dash by B0 into T0 by T0 dash. So M dash, that is equal to, take this M on right hand side, that is 15% of M maximum. 15% means 0.15. M maximum, that is 30. B0 dash, that is 0.98. B0, that is 0.64. T0, that is 4.2. T0 dash, that is 2.8. Now solve this one. You will get the answer in ampere meter square. Clear to all of you? 5.24. A Rowland ring of mean radius 15 centimeter has 3500 tons of wire wound on a ferromagnetic core of relative permeability 800. What is the magnetic field B in the core for a magnetizing current of 1.2 ampere? Rowland ring, that is nothing but the toroid. Right? Toroid is also called Rowland ring. Now see here, the mean radius for the toroid, that is given to you 15 centimeters, so that is 0.15 meter. Total number of tons, that is 3500. Relative permeability of the ferromagnetic core, that is 800. Now we want to calculate the magnetic field for the magnetizing current 1.2 ampere. Now see, we have the equation for the magnetic field inside the toroid, that is mu0 n I, where n, that is number of turns per unit length. mu 0, that is the permeability of free space. So when in the toroid, the core that is of air, or we can say free space, at that time we take the permeability of free space. But now suppose that air or free space that is replaced by ferromagnetic core, then we have to take the permeability of that particular material which one is used as a core. Clear the concept? Now B, that is equal to mu of material, means permeability of the core material, N into I. But mu, that is mu 0 mu r. Mu r, that is relative permeability of that material. Okay. So mu 0 mu r. Small n, that is the number of tons per unit length. This total number of tons, capital N, are wounded on the toroid. So we can say this much number of tons are on the circumference of the toroid. So total number of tons divided by total length, that is the circumference, that will give you the number of tons per unit length. So N upon 2 pi r into I. So here we can write mu 0 upon 4 pi mu r and I upon r, here multiply by 2 also. Now substitute the values. Mu 0 upon 4 pi, that is 10 raised to minus 7. Mu r, that is 800. N, that is 3500. I, that is 1.2. 2 as it is, upon r, that is 0.15. Now solve this one. You will get the magnetic field in the Rowland ring, or we can say inside the toroid. Clear? 5.25. The magnetic moment vectors mu s and mu l associated with the intrinsic spin angular momentum and orbital angular momentum L respectively of an electron are predicted by quantum theory and verified experimentally to a high accuracy to be given by mu s, that is minus E by m into s, and mu L, that is minus E by 2m into L. Which of these relation is in accordance with the result accepted classically? Outline the derivation of the classical result. So out of this one, which one is the classical relationship? So that is of magnetic moment, which one is in terms of orbital angular momentum. In previous chapter, we derived this equation also. Okay. See, if we consider the revolution of electron, then we know it constitutes the current. So magnetic moment, that we can write current into area of the loop. Current, that is electron charge E upon time capital T. When one revolution is completed, the amount of charge flow, that is charge of electron. Electron have negative charge, so minus E by T. Area, that is pi r square, where r, that is the radius of its orbit. Now angular momentum, that is mvr. So mv, that is the speed of electron. So when one revolution is completed, the distance covered 2 pi r in time capital T. So v, that is 2 pi r by T into r as it is. Okay. Now if we take the ratio of these two equations, So mu L by L, that is minus E by T pi r square into T upon M 2 pi r square, that is minus E by 2M. So we can write in vector form mu L, that is minus E by 2M into L. So this one is classically accepted. Now mu S, that is E by M into S in terms of spin orbital momentum. We can derive this equation on the basis of quantum mechanics only. And at present, it is out of your scope. Clear to all of you?